Yes, it's a foot. Most people have two of them. Someone once said feet are very necessary. They stop legs fraying at the ends. But the foot is just one of many works of nature that have inspired architects, structural engineers, and designers. Nature has often shown them the way to success. Sir Henry Wotton lived in the time of the first Queen Elizabeth. He was a poet, an ambassador, and a connoisseur. Inspired by earlier writings from the Roman Vitruvius and the Renaissance architect Palladio, Sir Henry spelled out in his book that good buildings must contain three important requisites or considerations. He called these elements commodity, firmness, and delight. In today's language, we would say something like suitability for its function, serviceability and safety, and good appearance or aesthetic satisfaction. And especially in tough financial times, we must add a fourth criterion, economy. Taken to an extreme, it is obvious a large building with a plain roof protecting those inside from the rain would not be expensive and may be used as a place of worship. But compare its appearance and atmosphere with, say, Canterbury Cathedral, which has the power to awe and entrance the beholder. There's no contest. But we must not forget, cathedrals didn't just happen overnight. It took us many, many years before we could build with confidence and build cathedrals to last for centuries. And even then, were any of those master builders able to predict what was going on within these huge structures, what was likely to happen? Today, we use words like stress, thrust, collapse. When we want to attach a heavy object to a wall, we usually drill one or more holes, fill the holes with wooden or plastic plugs, and attach the object with screws into the plugs. We know the screw will squash the plug against the sides of the hole and create what is called a zone of compressive stress in the plug and in the wall around it. And see how difficult it is, normally, to pull out a screw and plug from the wall. Frictional resistance has been generated. In other words, we've set up a permanent state of stress, which makes the structure or other load-bearing object work better than it would without the pre-stress. Next time you're lucky enough to see a spider spinning its web, watch closely as it pulls the threads tight. It's doing this to prevent lower threads going slack when something lands on the web. Without this tensioning, the web, with virtually no weight, could not withstand winds and the arrival of the spider's next meal. The clever spider has no idea it is adding tensile pre-stress. The threads are very strong in tension, but quite incapable of carrying compressive forces. The inventor of the modern form of bicycle wheel might well have taken his inspiration from the spider's web. Once more, it's tensile pre-stressing. The wire spokes very strong in tension, are so slender that under a very small compressive force they would buckle. No, each spoke must be kept in tension at all times. If one has the misfortune to buckle a bicycle wheel, it's a job for the experts. Turning the bicycle wheel into even more of a remarkable structure is its pneumatic tyre. Without air it is nothing, but inflated and pre-stressed in tension, it can carry many times its own weight. A particularly interesting example of pre-stressing is our ability to lift books, like when we transfer a row of books from one shelf to another. The trick is to know where to place one's hands. Halfway, and one needs to press harder. But instinctively we place our hands lower down and don't need to press so hard. We're actually causing the centre books to bend upwards, counteracting the tendency for their weight to cause them to fall. Finally, a very important area of this application in the construction industry is the pre-stressed reinforced concrete beam. Today one may see them used for many purposes. We often see them forming the main component of a road bridge over a river, as with this local example. The heart and strength of this bridge structure is the series of 9 pre-stressed beams laid parallel. Shaped like the letter I, each beam is placed upright and rests on rubber blocks at each end. On these 9 beams is laid the road surface, the footpaths and the walls on either side. In this example, it's interesting to see the designer's decorative use of brick on the outer side of the bridge wall. Notice the slight, not unattractive, curve of bricks with a simple design placed above the centre of the river. Surely a modern interpretation or representation of a bridge from earlier times, an arch with a keystone. Too bad most users of the bridge are not able to observe the results. Use of pre-stressed concrete beams took off after World War II. Improved quality of the concrete and better choices of steel led to better reliability. I remember a road engineer introducing me to the remarkable qualities of a pre-stressed beam in the mid-1950s. He explained how, in those days, the simple moulded beam of concrete containing a skeleton of steel reinforcing also contained end-to-end lengths of special steel which, when fitted with screw threads and special attachments at each end, could be used to compress or pre-stress the beam. In other words, the concrete is permanently compressed. There are no cracks and therefore no fear of corrosion. And my friend the road engineer demonstrated a curious phenomenon of such beams. Using a beam resting on trestles and about to be lowered into place in a new bridge, with one blow of a hammer, the beam rang not with a dull thud, but with a musical bong. Incidentally, it will have been realized that pre-stressed structures are different from other kinds of structures in that they are permanently under the action of heavy pre-stressing forces, which literally hold them together. It has been realized that should corrosion of the reinforcing steel proceed far enough, and because it is so well protected, inspection is virtually impossible in most cases, it could break at the worst affected point. The pre-stressing forces could be released, and the concrete could fly apart without warning and with explosive force. Attempts have been made in recent years to check for this problem, but the general consensus is that only time will tell. As well as studying nature for ideas on how to solve a problem, designers and builders are often reminded by nature on how not to do it. First, there's the ill wind. No, not the musician's tale of the one that nobly blows good. We're talking about the natural force of wind and its effect on structures. John Smeaton was one of the earliest of the modern designers. He completed the first successful lighthouse on the Eddystone Reef off Plymouth in 1759. And just like anyone who is successful, his comments and judgment on natural forces were thought of as gospel. Smeaton said wind pressures would not exceed 12 pounds per square foot. And everyone, so it is said, accepted his dozen pounds, but we know now the Eddystone Lighthouse has been battered with winds 4 times as strong. Which leads us to the tale of a famous bridge disaster. Engineer Thomas Bush had been commissioned to design and build a rail bridge across the River Tay. He did think about what effect the wind would have on his nice new bridge. He had consulted the Astronomer Royal of the time, Sir George Airy, and was told in a letter that 10 pounds per square foot was all that was needed. So Bush, as he said at the inquiry, made no special provision for wind pressure on this very exposed structure. As history records, a stormy night in December 1879 did away with the bridge, together with a steam locomotive and its train, with all 75 lives lost, and the reputation of Bush. And this was only 18 months after completion, during which time Queen Victoria had crossed it by train and Bush had been knighted. It's interesting to note that contemporary US engineers were using 50, the French 55, and a few years later, 56 pounds per square foot were used for the Firth of Forth rail bridge, a number that's not unlike the one used today in similar situations. And Sir George, Airy by name, after the accident he's reputed to have revised his advice upwards to no less than 120 pounds per square foot. According to the parable in the New Testament, wise men in biblical times built their houses on the rock, and this remains true even today. But what about foundations elsewhere? The answer lies in the soil is not just for gardeners. Given the job of supporting foundations, most soils will be expected to settle, and some, such as clay soils, have been known to have a life of their own. Add water, or remove it as in a drought, and expect some surprises. Soil mechanics, as they are known, came into being around the time of the First World War, when an Austrian engineer, Karl Terzaghi, carried out his first experiments on the strength and compressibility of soils. So, until relatively recently, designers used past experience, often written down as vague descriptions of types of soil and what stresses they might be expected to bear. It is said some earlier, less gifted designers planning buildings used a mix of engineering judgment, intuition, and a few pokes in the ground with a walking stick. Today's way round a foundation problem is often the building of a raft, which then spreads the load. In very poor ground, piles are driven deep into the ground, ideally until they reach rock. Actually, Venice and Amsterdam would not exist without their pile foundations, although Venice is a spectacular example of what is known as foundation settlement. The weight of a building squeezes out the water under it. The building sinks a bit, and eventually the ground stabilizes. But in the case of Venice, they need to find more drinking water. The Venetians' water supply originally came from the mainland, but from 1910 onwards, this was supplemented by boreholes sunk to the depths of more than 300 meters in the clay under the city. The result? Disaster. A general subsidence. Since the walls of most Venetian houses start only about a metre above average sea level, and no builders thought to include a damp course until after 1800, even a settlement of between 10 and 20 centimetres can be very destructive. Pumping has stopped. Buildings have stopped sinking. But if you're a first home buyer in Venice, expect the surveyor to include an interesting warning in his report. Mexico City has become an even more bizarre example of this problem. Much of the city is built on what remains of a dried-up lake. This 30 to 40 meters deep, soft bed has been drained over at least 3 centuries. So when the builders started, stability had been reached, and settlement was no problem. Unfortunately, in the 1800s, there were water shortages, and soon pumping started from deep wells. Between 1900 and 1980, the ground level in the centre of the city sank in some parts by as much as 6 meters. Older buildings on shallow foundations had gone down with the general subsidence. Many of these sunken buildings were at all angles, and cracked sewers, water pipes, and pavements created endless problems. But the problems did not stop there. Modern multi-story buildings on piled foundations had not settled. So there they stood, together with the iron casings of the wells, high above the sinking buildings, as pumping continued. Sometimes, no matter how hard one tries, no amount of checking and double-checking of the calculations will prevent a disaster happening. Brilliant in conception, and looking on the architect's drawing board like the billowing spinnakers of the yachts in the harbour, the sections of the Sydney Opera House were intended to be built as thin concrete shells. And on a small scale with strengthening, they would have stood up under their own weight and the force of the wind. But the colossal size ruled against it. More strength had to be built into the superstructure, which led to stronger foundations, which led to the departure of the architect, a longer building time, and considerably increased costs. Fortunately for those playing the bill, Lady Lucky contributed. Revenue kept rolling in from the special weekly lottery run by the Government of New South Wales. Another curious example of a mix-up in the calculations is the rail bridge which crosses the river Wupper at Mungsteiner between Solingen and Ramscheid in the Ruhr area of Germany. One of the highest rail bridges in Germany, it was built in 1897 and named the König Wilhelm Brücke. A fine name for a fine bridge, until it was realized one small miscalculation at the planning stage had created a structure that would forever be the target of jokes. I mean, no one likes making mistakes that are public, and no doubt those responsible who put it together during the reign of Kaiser Wilhelm of World War I notoriety, probably never lived it down. We have ways, etc., etc. And the joke? Someone forgot to include the weight of passengers when calculating the weight of a passenger train crossing the bridge. So we're told, passengers left trains at stations before the bridge and crossed the river by some other means to rejoin their train later. Nowadays, a smallish, lightweight two-coach diesel railcar crosses the bridge with Deutsche Bundesbahn precision every 30 minutes with passengers. With architects, engineers and designers, there are constant referrals in their work to stress. At this point we can wheel in Diplodocus, a dinosaur which roamed North America during the late Jurassic period. Think of the development of his long tail matching his head on its long neck, and straight away there's a modern application. There's little doubt during the process of evolution over time that the weight of these huge creatures was gradually concentrated where it could cause the smallest forces in the skeletal system to enable them to grow as large as possible. And the result? It has been calculated the weight of the largest dinosaurs was disposed in a way remarkably like the double spans of modern very large cantilever bridges, such as the very famous one of 1890 crossing the Firth of Forth for the railway. Over the years there has been a tendency for the suspended span to become smaller and smaller in relation to the other spans. There's talk of some large span European highway bridges where this tendency has been carried to the limit, the suspended span being replaced by what is known as a hinge, which directly connects adjoined cantilever arms. Ever wondered why scaffolding is invariably made of steel tubing? It's because a hollow circular tube is better able to resist bending in any direction. But nature did it earlier and better. The stalks of slender plants like grasses and bamboo, which must stand up to wind, are hollow tubes made of fibre. They're strong, so much so that in some areas of the world lengths of bamboo are used for scaffolding. And in our own bodies, the bones of the leg and arm, which are stressed in bending, are also hollow tubes, which do a double duty as handy storage areas for fat and for the production of blood cells. There are other methods of increasing resistance to bending in materials. Obviously, a flat sheet of almost any material will bend and warp if held by only the edges. But given the same sheet a series of bends in parallel, and we have corrugations, sometimes iron, plastic, but in this case paper. It supports itself quite easily and will even carry a weight much heavier than itself. What's happened is that the corrugations have turned the flat sheet into a beam, so reducing the stresses. Of course, once more nature was first. Mollusks such as the scallop are one mass of corrugations. A close relative in building terms is the shell roof, a building form with many variations. Cylindrical shell roofs are often used for factories. Built in parallel, each shell roof supports its neighbour laterally, and this prevents the spread which would allow bending to develop. The coiled shell of the pearly nautilus, with its intricate inner chambers, or even the shell of the common garden snail, they're perfectly adapted to the life of the occupant. And many structural designers have realized these forms have a remarkable strength. The influence of mollusks' shells can be seen in many modern buildings. With every building project, especially those out of the ordinary, the little matter of stress paths is sure to be on the agenda of the structural engineers and designers. In natural structures, one of the most remarkable instances of stress paths occurs in bone structure. In much of the bone of most mammals, the hollow interior is filled with a fine latticework of interlaced bone called cancellous tissue. It appears we are indebted to a Professor Kuhlmann of Zurich. He had been sketching what are called stress trajectories in a curved crane head he was designing. As this was in 1866, everything and anything was possible. The professor looked across the room and saw an anatomist colleague sectioning a metatarsal bone, the same shape as his crane head. Immediately it flashed through the professor's mind. The arrangement of the cancellous tissue was just like the stress path he had been sketching. "Eureka!" he said, or something similar. Nature was strengthening the bone in precisely the manner and direction in which strength was required. The same phenomenon is found in any other bone which has to carry weight and resist bending. It is particularly clear in the bones of the human foot. In conjunction with the muscles of the sole of the foot, the bones act very much like a triangle roof truss of the same shape. But this same idea can be traced in other bones, and in all cases the alignment of the cancellous tissue follows the stress trajectories. And there is an explanation for this remarkable phenomenon. The growth of organic stress-resistant fibre is encouraged by direct stress. As the baby develops and rises to its feet and walks, the bones in its feet grow stronger every day in parallel to growth of the body. One can see it in the fibres of an apple stalk, thickening rapidly as the fruit grows in weight. Similarly, the trunk and branches of a tree are thick in proportion to the direct and bending stresses they have to carry. Also, the cell fibres are aligned strictly along the lines of stress, up the trunk and along the branches. So next time you see a Diplodocus in your garden eating the apples, with its tail some 6 gardens away, you'll remember it was an early example of the cantilever principle.